Hi, my name is Leo Rivera. I'm the Director of Scientific Outreach here at Meter Group. And today we're going to talk about particle size analysis measurements, and we're going to focus on the technology and methods behind those measurements. Just to preface this, in a previous video, we talked about some of the fundamentals behind these measurements. And one of the things we really focused on is Stokes' law. And just a brief summary, Stokes' law allows us to relate the settling time of different particle sizes in solution to the particle size that we're trying to measure. And some of those common techniques that are used for measuring that settling time are the hydrometer method, the pipette method, and the integral suspension pressure method. And today we're going to focus on all three methods and the ins and outs and the pros and cons of each method. But it's really important to kind of look at the measurement zone for each of these methods to help you understand what you're measuring, so you can see the measurement zone for the pipette method versus the hydrometer method versus the integral suspension pressure method. So now we'll talk about the hydrometer method. And the way the hydrometer method works is it uses a tool called a hydrometer that is typically used to measure the density of a solution. And we're using that tool to measure the change in density or the settling depth of the hydrometer over time. And then we're relating that settling depth over time at specific measurement intervals to the different particle sizes that have fallen out of solution to help us figure out what still is remaining in solution, and then to help us figure out what the actual particle size distribution of our soils is. And you can see here kind of that equation that's used to help us relate those measurements. But some things to think about with the hydrometer method is typically you have to make a measurement of the solution, and we also have to make a secondary measurement of what we call a blank cylinder to correct for the temperature of the solution at that time and the dispersant that's been added to the solution. That typically we're adding dispersant to help separate those soil particles. We need to understand the impact of that dispersant on the measurement. You can use the hydrometer method to try and estimate your sand fraction initially, but typically most of the sands fall out of solution within the first 30 seconds. So it's really hard to get an accurate measurement of the sand fraction based on this method. So typically it's best to separate the sand fraction and measure that separately by wet sieving and then using our sieve analysis to get the sand fraction of the soil. The hydrometer measurements typically take around 24 hours from the start of the settling time and involve several measurements in between that 24-hour period to get our different particle size measurements that we're trying to get. Some of the challenges with the hydrometer method, well, one, as you can imagine, these are manual readings, right? So manual readings are often error prone. One technician can read something different than another technician, and so that can create challenges. They do have fixed measurement times, so that means you have to be there from the start of sedimentation at specific intervals to get an accurate measurement. And you have to be there at those set times to really get an accurate measurement based on that. Also, if you're only using one hydrometer and going from each cylinder to make multiple measurements over time, if you have multiple cylinders set up to make those measurements, the disturbance of the sedimentation process from inserting the hydrometer can also create errors in the measurement. Typical accuracy for the hydrometer method is about plus or minus 3%. And one other challenge with the hydrometer method is the dreaded 24-hour reading. And I brought this up. This was a tweet from a soil scientist who's doing hydrometer measurements, and he posted Saturday morning hydrometer method, the 24-hour reading. And that's an issue. One of the challenges with the hydrometer method is, again, like I said, we have to be there at set intervals. And so that means we need to get that 24-hour reading. And that could be on a Saturday. It could be at really weird hours that you need to make those measurements. And so those are just some of the challenges with the hydrometer method and making those measurements. So the next method we're going to talk about is the pipette method. And the pipette method is often referred to as the gold standard method for Stokes law-based measurements of particle size analysis. And it differs a little bit from the hydrometer method where we're trying to measure the density of the solution. Instead, we're just taking small subsamples from that solution that has the soils in suspension as they're falling out to measure the different particles that have fallen out of solution at different times. And typically we're breaking those times up to target the 2 micron, the 5 micron, and the 20 micron size particles based on those measurements. Similar to the hydrometer method, we need to separate the sand fractions and measure that separately based on our sieve analysis. The nice thing about the pipette method is that a typical measurement time is about 6 hours, so it's a little bit faster than the hydrometer method. And typically it has similar levels of accuracy, but we don't have as much error associated with trying to measure the density that we might have with the hydrometer method. So some challenges with the pipette method is, again, you still have some manual readings. You're having to pull the sample from the cylinder and pull it in a consistent amount of volume. And the timing, again, is somewhat critical here. And then we're going to measure the amount of soil in that solution that we've pulled out at set times to try and get what is remaining in suspension. And so there can be some errors with the weight measurements and things that can happen there that we typically expect to see with the pipette method. And similar to the hydrometer method, we still have issues with the disturbance of the sedimentation process from inserting the probes. The pipette itself is a little bit smaller, so the disturbance is also smaller, but that process of actually extracting a sample from the cylinder does disturb the sedimentation process a little bit. So there's some potential errors there. And the typical accuracy of the pipette method is still plus or minus 3%. So again, not a huge improvement in accuracy, but it is still referred to as the gold standard method for making these measurements. So the last method that we're going to talk about today that's based on the sedimentation approach is the integral suspension pressure plus method, or the ISP plus method. And the way this method works, instead of a hydrometer, we use a high precision pressure transducer to measure the density change of that solution in suspension as the particles are falling out over time. And then through inverse modeling, we're relating that density change over time to the particle size distribution of the soils from that measurement. Something I think that's really important to point out is something that changes because of this approach is that our volume that we're measuring is much larger. So here you can see that sampling zone. And if you remember that from the earlier methods that we showed, this is a much larger sampling zone than what we typically make with the other measurement methods. And that's something that actually really helps improve our accuracy with this measurement method. Now, just like the hydrometer and the pipette method, we always recommend separating the sand fraction separately and measuring the amount of sand through separate analysis, typically using the sieves, just like with the other methods. Again, because the sands fall out of suspension so fast, it's really hard to catch this measurement. Diving a little bit deeper into how the integral suspension pressure plus method works, it is an extension of the original ISP method. We don't talk about that much because this is the new method that we recommend. At a specific time interval, part of that suspension is drained and then oven dried, and you can see an example of what that looks like here. And this really improved the accuracy with the integration of the drain suspension to really hone in on the clay content and get a more accurate clay content estimate. And what's really nice about combining all of that with the pressure transducer measurement is that now the ISP plus method decreases the measurement time to 2.5 hours versus the 6 or 24 hours of the pipette and hydrometer method. And it improves the accuracy to plus or minus 0.5% versus the plus or minus 3% from the more traditional methods. So you get a really significant improvement in the accuracy overall of the measurements. I think it's really also important to look at what the typical data looks like from the ISP plus method. So here you see an example of the pressure measurement and then how we've derived what the cumulative particle size distribution curve looks like based on that inverse modeling. And here you can see an example of that cumulative particle size distribution curve based on the ISP method versus what we get from the pipette method, which is shown in the blue dots here. And so you can see, one, how well these methods compare, but also you see the level of detail that you get from the ISP method or the ISP plus method versus the point measurements that you get from some of the traditional methods like the pipette method. And so as our soils become more complex and we see a little more complex curves, this gives us more information on what that soil actually looks like and what that might mean in terms of how the soil is going to behave for some of the different processes that we're going to be trying to understand. Now, just like all of the other methods, there are, of course, challenges with the ISP plus method as well. It's really dependent on precise electronics. And I don't know if you noticed in the graph earlier, but the pressure level that we're measuring is to the Pascal level. So really precise measurements of pressure that we need to make. And of course, there's still potential sources of error in the measurement. There can be user error in the dry mass calculations, which we can always try to limit. And it does require temperature equilibrium. So ideally, we're going to see less than 1.5 degrees change in temperature over the duration of the measurement, which can be done in a temperature controlled lab. And there can also be errors in the sand fraction estimate, just like with any of the other methods. And so always our goals are going to be to try and reduce our errors in these components of the measurements to have as accurate of a measurement of particle size distribution as possible. So we've covered some of the methods for measuring particle size based on the sedimentation approach. In our next video, we'll talk about some of the optical methods and ins and outs of those approaches.